Engineering 305, example problem, chapter 6, number 9. I just noticed, I was looking in the book, and there is only one paragraph. I was complaining last week about there being only two paragraphs on power. This week on statically indeterminate, there's only one paragraph in the book on statically indeterminate. But the parallels between this in torsion and what we did in axial loads, very relevant. And so there aren't any new equations. We're just going to apply everything that we've learned to this class of problems. So let's bang through this one. This is example problem 6.9. A hollow circular aluminum alloy, so they give us material properties, has a steel core. So that's an interesting thing, as shown in figure 620A. And I copied that from the next page and put it on you can see it, right? The steel and aluminum parts are securely connected at the ends. If the allowable stresses in the steel and the aluminum must be limited to 14 KSI and 10 KSI respectively, determine, let's just start with that. What's the maximum torque that can be applied to the right end of the composite shaft? So, and then we're going to talk about what's the magnitude of the rotation. But those are the two questions that we've got. But we're starting with what's the maximum torque that can be applied at the right end of the composite shaft. Well, all right, let's get rid of a problem statement. I think that's going to be button 1. Oh, I got to get rid of that. 3, and sorry, that was 4. 3. Let's keep my picture there for a little bit. I probably should have left the problem statement up because I didn't write down the material properties. But we'll get to that at the end when we start plugging stuff in. The question was, what's the maximum shear? What's the maximum torque that can be applied? I've got a 14 KSI limit in the steel and 10 in the aluminum. So, pen's not working. Stress in the aluminum is equal to 10 KSI, and the stress in the steel is equal to 14 KSI. All right, so what is that? I just wrote it down wrong. Well, that was even. I got to keep my stresses right. How did that problem statement read? Why am I thinking sigma? This is my shear in the aluminum and my shear in the steel. Let's take a look at that problem statement again. The allowable stresses must be limited to steel and aluminum. I don't know. Oh, wow. I don't know what they're asking. I don't know whether they're telling me the maximum shear stress or the maximum normal stress. Of course, I'm going to go back because one of the things we learned is if it's a torsion only problem, then Moore's circle looks like that. So that would be the maximum allowable, and this would be the maximum allowable, and they're both the radius away. So it doesn't really matter. The maximum stress that is allowed is either the normal stress or the shear stress on a torsion problem. So there we go, maximum allowable stress. Now, that stress in a torsional member is Tc over J. And that is true for the aluminum and it's true for the steel. We already know, I don't know what the load is in the two pieces. What I was going to say is if I knew what the torque was, then I'd be all set, but I don't. So this is the torque in the aluminum, shear C A. That's the equation for the aluminum. And then I have to have the same equation for the steel. I'm going to hit my F11 a sec, make that go full page. Just like that better. Torque of the steel, C of the steel, J of the steel. Now, I do have geometry. You can see that I've got geometry. I've got a 2-inch steel core and a 4-inch outside. So, hold on one sec. All right, back at it. So I could start punching values in because I know enough to know Well, I'm going to say I know this and I know that. I know CA. I don't know. Well, I'll go through it, right? Like normal. There's one unknown. Here's two unknowns. Here's three unknowns. Here's four unknowns. And unfortunately, that goes back to I've got 1, 2 equations. So what's my next known? I know that the torque in the aluminum plus the torque in the steel is equal to, well, whatever torque is applied total. I guess it doesn't really help me. At some point I want to figure that out, don't I? That just adds another equation and another unknown. I don't really think that helps. Let's keep plugging away. I know that the deflection of the steel is equal to the deflection of the aluminum. Now, technically, that did add 2 more unknowns, 5 and 6. Gave me one more equation, that's number 3. But then I have, in blue, theta of the aluminum equals torque of the aluminum L over JG, and I got to put, oh man, I think L over J aluminum, G the aluminum, and theta of the steel is equal to, let me get rid of this for you. Took a couple tries. Theta of the steel is torque of the steel, length of the steel, J of the steel, G of the steel. So now, did I add? This did not add any new unknowns because I've already identified those. But I did get equations 4 and 5, and now I actually have 2 other equations. If I go back up here, either this one is true or that one is true, and I don't know which. That's the bummer. One of those 2 is true, and so I think I'm going to get away without, I'm never going to use that. While normally that's an equation that I use, it is not in this case. So, do I just start substituting? I guess I could just start substituting in and going crazy on this. That would be, so let's outline this method, because again, think, it kind of goes back to what I'm teaching in 181 right now. When you want to draw something, have a strategy for where you're going to start, where you're going to go, so if I were going to do that, then I would say, here's my process. I'm going to say equation 1, solve for TA. Because that would, if I put that in, that would be 1 equation, 1 unknown, so I could solve for TA. Then I would take step 2, I would go with equation 4, and solve for theta A. And then 3, equation 5, use theta A equal to theta S and solve for Tia, the torque in the steel. And then 4, I'm going to validate the shear in the steel is less than the shear allowable. And if that's true, then I'm all set. If true, I'm done. Else, I'm going to go back in. I'm going to use equation 1. Nope, I'm not going to use equation 1. I'm going to use equation 3, and I'm going to start now with the shear in the steel.
and maybe that's what I said. Using shear in the aluminum is equal to T in the allowable for aluminum. And if not, then I start over. Then step 5 would be equation 2, solve torque of the steel using torque of the shear. Let me rewrite that. Shear in the steel is equal to shear allowable for the steel. All right, that's my process. So step 1, solve equation 1 using the shear that's allowable for the aluminum. Shear allowable for the aluminum is right here. So that's going to be these two equations are going to, those two are going to allow me to solve for the shear, for the torque in the aluminum. I just don't like solving problems in red. Torque in the aluminum is equal to shear aluminum, allowable in the aluminum, J over C, right? That's my rearrangement. Tau J over C. You can't see that when I point at the screen. You have no indication of where I'm pointing. One weakness of this technology. Maybe we need to figure out how to do a laser or something on this. And then I'm going to just substitute in. And this is going to be a really long video, so I'm going to skip some of these steps. So I'm going to pause it, solve it, and put the answer down. And you could pause it and redo the calc on your own. All right, so I did that. I calculated that out. There's my J is pi over 2. Remember, you got to use the radius to the 4th, not the diameter. I almost made that mistake. And then C is the radius. And I got 117,400 pounds. Okay, great. Now then, step 2 was going to be I'm going to solve for theta A, which is equal to T L over J G. I already calculated J. I know what G. I got to go write down G. G comes from my problem statement. G is 4,000 KSI. 4,000 KSI? 4,000 KSI. And so I know TLJG. I don't know. Actually, I don't know. It's 60 inches long. You see that on the picture? Yep. Okay. L is equal to 60. Be right back. All right. So I gotta get my screens. There we go. I calculated that, and you're seeing boom there. And one of the things as I was doing that, I was doing units, and I hadn't put inches here. I had a force in pounds. It's a torque in inch pounds. My units failed to cancel, but that was correct. And part of the reason I didn't get that is because I didn't run this calculation out, which led into when I needed that here. That caused me to figure that out. So that was step 2. Step 2, solve for theta A. Now I'm going to go find. I know what that theta S is. So now I'm going to solve for the torque in the steel in inch pounds. That torque in the steel is equal to, well, I just got to rearrange this equation. So it's going to be theta in the steel, which is equal to the aluminum, JG over L. But I have one more thing. Now I've got to do J for the steel, which is equal to pi over 2 times 1 to the 4th, because the the radius is 1. So that's nice. That's pi over 2 equals 1.57 inches to the 4th. Get my units in there. I know L. I got to look up G. Wrong one. G for the steel is 11,600. G is equal to 11,600 KSI. All right, let's theta J G L is 60. Let's go calculate that. Okay, I got the The torque in the steel is 22,461. Now I got to go validate that the stress in the steel is less than the allowable limit. And so I have to calculate the shear in black. Shear stress in the steel is equal to TC over J. Again, now I know here is my T, and I got J, and I got my C, which is now a 1/2 inch. That's the only problem there. So it's I'm going to calculate that. Hold on. So first thing I did, I just told you that C was equal to a 1/2, and it's not. C is equal to 1 for the steel, and that's the diameter is 2. I was thinking the diameter was 1, so I screwed that up. But anyway, so I put it in correctly, and I got that answer. Now the problem becomes if the allowable stress is 14,000, and I am at 14,300, so this is too high. And they set this problem up just for that. But if we had gone the other way, if we had chosen to work the steel side of it first and then the aluminum, we'd be all done now. But we're not. Now we're not. So now I need to repeat the process that I set up going the other way. And so that means I have to put in 14,000 is equal to TC over J. And then T is equal to, speed up time, 21,990. Just look at that. Look at how much, look at the difference in, put the units in there, compared to what I was working with. I am 500 inch pounds different. It's ridiculous. So anyway, that's my new torque of the steel. And so then I get the deflection in the steel, which is equal to the deflection in the aluminum, is equal to TL over JG, which is equal to, speed up, equal to the 0.0724 radians, which then I take that and I say that the theta in the aluminum, actually, that's not the way around it. I need to find the torque in the aluminum is equal to theta in the aluminum JG over L, which is equal to, 113,750, which compares, before I had 117,000. So I'm really, okay, so now I'm 4,000 different. And now using that torque, I can get the stress, in black. Oh my goodness. The stress in the aluminum is equal to TC over J, which is going to be equal to 9,000. I got to look at my number again. 9,660 KSI. Sorry, PSI when I write it out. RSI, PSI, or 9.6 KSI, which is less than 10 KSI, which is equal to the stress allowable. So this is good. So in other words, I've checked out that situation. So you checked. So that condition is held up. So I'm all good. So that solves. So let's go back. What's our question? The maximum torque that can be applied to the right end of the shaft. Okay, well, if I look, the torque in the aluminum is equal to 113,750 plus, that's just the torque in the aluminum. The torque in the steel is equal to, I got to scroll back, 14,306. Inch pounds, and then all the way at the beginning, I wrote down this equation I said we wouldn't use, right here. The total is the sum of those two, which is 128,000 kip inches. right? 113. Sorry, I might have wrote down the wrong number. I wrote down, that's not the torque. You guys saw that right away and were laughing at me. Count on your partner. Here's the torque right there. 22,461. 22,461 inch-pounds, which that adds up. See, now I got to add all the way 1, 1, carry the 1, 2, carry the 1, 6, 136, 211. Yeah. I wonder if I even wrote down the wrong number there, because actually the book, I'm looking at the book as I do this, the torque total is equal to, they've got 135, so they have my 113,750, and then they use 21,990. So what did I use? Oh, I grabbed that up there. Yeah, this is the torque I was supposed to use. That was too high, 22,460. I had to drop that by 500 pounds. So this drops. Let's try that a third time. Let's go with magic colors now. That's the torque of the steel. 21,990. 21,990 inch-pounds. And then that makes the total. Boy, after all that effort, it'd be nice to have a calculator built into this whiteboard. But, you know, you take what you get. If I add 122, it's going to give me 135 kilo-inch-pounds. Okay, that's my total torque, which was question 1. That's the total torque. What's the magnitude of the rotation? Well, we solved that actually 2 times. The second time we solved it is right there. That is the lower of the two. The other one was 0.074. That was too high. We wound up getting 0.0724. So that is the rotation, part B. Theta is equal to 0.0724 radians. All right, there we go. Whew! Long problem, huh? Long problem. Even with, and I cut out all the calculation stuff you didn't see. And then I did some calculations I wish you hadn't seen. But, you know, count on your partner for one. So if you guys had been sitting next to me, you could have caught the mistakes earlier. Hope you're doing well. Don't worry, there's more. Next lecture is on, I think I'm going to non-circular sections, which is kind of fun for me, but it can be confusing. So, talk to you later.